All right, so let's review a little bit of polar coordinates before we go on and do this with our calculus. So remember back in pre-cal, you had to graph a polar coordinate like this. And so the first thing right here is the r value, and this part right here is a theta. So it's the angle. So remember, r is the circle, because in polar form you have these circles on here, like this is circle 1, circle 2, circle 3, circle 4, and then you have this angle to do right here. And so 0 to 2 pi over 3 would put you over there. So when you graph a point like this, you are going out to circle 5, so that would be this kind of blue darker circle, and then so I'm going out to this circle right here, and then I'm going over to 2 pi over 3, so I'm going over to right here. So this coordinate that's mentioned right here would be right there where that blue dot is. All right, and so when you graph an equation in polar form, when you graph a circle in polar form, you would just have something like r equals, let's say, like 2. If I was going to graph r equals 2 in polar form, I would go to circle 2 and I would just go like this. So this is like compared to, say, in rectangular form, I would have x squared plus y squared equals r squared, so 4. So you see it's like this right here, these two mean the same thing, they're just in different formats or different coordinate systems, and you can see how r equals 2 is like way simpler, right? So then we have these formulas for going back and forth between the two coordinate systems. So these 3 formulas right here, plus there's one more, that would also be tangent theta equals y over x, are 4 good formulas to have on your your note card or something. So like that other point that we had before, we had 5 and 2 pi over 3. So remember, what you would do with those is you would take this r and this theta and you would plug them into the formula, say for x and for y. So if I wanted the x value, I would say, oh, x is just r, which is 5, and the cosine of 2 pi over 3. Well, at 2 pi over 3, the coordinate is, let's see, it's negative 1/2 and then radical 3 over 2. So I'd multiply this by negative 1/2 because that's the cosine at 2 pi over 3. So my x value is negative 2.5. And then the y value would be r sine theta. So I would have 5 times radical 3 over 2. So basically I get y equals 5 radical 3 over 2. And so this xy, if you were to graph this on an xy coordinate system, if you went left negative 2.5 and up 5 radical 3 over 2, it would put you basically in the same spot that this puts you right here. And so it's just the same place but different coordinate system. Okay, so anyway, these 4 formulas are like going between the different worlds, is how to equate things in one world to the other. And then down here's some of the different some of the different equations that you had before. A cardioid, right? Lemniscate, rose curves, and a spiral. We're not going to use the spiral really, but anyway, you see some of those pictures start to appear. All right, so when we go ahead, let me talk about this other page first right here. So remember back when we were doing x and y, if you had something, if you had a space, like let's say you had like a little triangular shape right here, and you were trying to basically make up an integral for this shape right there, right? So if you had that thing, you could choose to do it 2 ways. You could go top to bottom, because that's what we're kind of used to. So when we're doing that, you would say, oh, I'm going, the bottom right here, that's star to, I don't know, star 1 to star 2. And so you'd put, star 1, star 2. And then you would have dy, because you're going in the y direction. And then you're going, let's say, from 0 to 4, I don't know. And then you had dx. Well, you could have also done it instead with dx. If you're going, right to left, or left to right, you could have had, let's say, smiley face 1 and smiley face 2, right? So you would have put smiley face 2 down here and smiley face 1 up here. And then you would have put your y values. Let's say that the y values went from 0 to 3, let's say. Okay, and so that's what we've been practicing, whatever the integral was of, whatever that was. But so you could do it 2 different ways. And so when you're doing this with circles and R equations or equations in polar form, you can also do this 2 ways. You can go from one angle to another angle and then choose to go from a radius to a radius, or you can go from one radius to another radius and then go from angle to angle. And so that's the way that we're going to do it. So we are always going to be doing this way. We are going to always do dr. So we're going to go from an r value to another r value, and then we're going to go from a theta to another theta. So we're going to be going from one curve to another curve and then going from one angle to another angle to get our space in between. All right, so anyway, that's exactly what this page is talking about as well. So recall, and if you recall or not, there's a formula for the area of a sector. It's 1/2 r squared theta, and theta has to be in radians. All right, so if I want the area of a section, like this section right here, I would basically need to do the area of this whole sector, right? And so that would be represented right here, minus the area of this little sector right here, represented there, and then subtract the 2, right? And so you could see that these things both have theta 2 minus theta 1 in common, because that's the angle that we're doing. And you see that these things both have a 1/2. So what is being done right here, we are factoring out the theta 1 and theta 2 and the 1/2, and then what's happening is that theta 2 minus theta 1 is turning into delta theta, and then the 1/2 is for both of them. All right, so that's just a little transformation there. Then notice when you have this r2 squared minus r1 squared, then that is simply factorable into a plus and a minus of the same 2 items. And when we have r2 minus r1, that turns into delta r. Okay, so here's the next little part right here. So 1/2 r2 plus r1, that is, when you add 2 things and divide by 2, that's like your average of 2 things. So that is basically kind of like the average of this radius right there. And so that is going to be denoted as r. So what you end up getting, and the whole purpose for this, is that delta A, or the change in the area, is going to be this r bar, and then, because that's what this piece is right here, all this piece right there, and then delta r delta theta. So this is supposed to kind of help you see that when we go to do an integral in polar form, a double integral in polar form, you always have to put an extra r in your problem. When you transfer from rectangular to polar coordinates, it's kind of like a change of variable thing that you have to do. You always have to put an r right here, and then you have your dr d theta that we're going to deal with. So that's it. When we're going to write these integrals, we always have to put an r in front of or after our problem, or multiply by an r, and that's all you just have to remember. So you see it right here and right here. Okay, so let's see. This is just explaining that you can do these things either way, dr d theta dr, but we are going to mostly do ours this way. Okay, and here we go with our first one. So the first thing to do is to kind of figure out what it's talking about. Don't worry about this xy, we'll take care of that in a minute, but we want to see that the region that we are trying to evaluate over is in the first quadrant, and it's between these 2 circles. So we're going to go ahead and draw that. So I have my 2 circles. So I got a circle with radius 2, and a circle with radius 5. And it's in the first quadrant, so this is the space that we are trying to like do the volume of with. This is our basically our like our height in a way. All right, so here we go. So double integral, I put xy, we'll worry about that in a minute. Let's see. So I want to stay between circle 2 and circle 5. So I will put my r and my dr and my d theta. I want to stay between r equals 2 and r equals 5. And then we are going in the first quadrant. So we're going from this angle to this angle. Well, if you remember back to your unit circle, that would be angle 0 to angle pi over 2. And so look how easy that is on our boundaries right there. Instead of doing circles where I'd have to do like, if I solve this for y, I'd have to do like the 4 minus the square root of 4 minus x squared, and this one, you know, square root of 5 or 25 minus x squared, sorry. And so it'd just be really horrible to do the integral that way. So right here, I have x and y. Well, I can't keep x and y like that. Remember that x in polar form is r cosine theta and y is r sine theta. So I have to change those. So if I basically am going to multiply those two things to replace this, so I have 0 to pi over 2 and 2 to 5. X is r cosine theta, y is r sine theta. So when I multiply these, I'm going to get r squared, cosine and sine. And I have this other extra r right here as well. So I'm going to have r to the third by the time I'm done, and then I have cosine theta and sine theta. And then dr, d theta. Okay, so these are just pretty much separate things. I'm just going to look at this r right here and integrate it. I would have r to the 4th over 4, and the cosine and the sine will follow me, but I'll have to evaluate this for r equals 2 to r equals 5. And so the cosine and the sine will just sit there. So I'll end up getting 5 to the 4th minus 4. 5 to the 4th over 4 minus, 2 to the 4th over 4. And then the cosine and the sine are just going to stay there. So if I, let me look at my answer here. If I just kind of subtract those, it comes out to 152.25 or, and so that's just going to go in front. I still have my one integral left to do, 0 to pi over 2, and I still have d theta. So let's take this up here. I have 152.25 integral 0 to pi over 2, and I still have cosine theta, sine theta, and d theta. All right, so I have to do a little bit of u substitution. We're going to let u equal to sine theta, because then du is just cosine theta, d theta. So all I'm integrating here is really the integral of u and du, because my cosine theta and my d theta are my du, and then sine is u. All right, so the integral of u is u squared over 2. So it's going to be sine squared, basically, over 2. And remember, I still have my 152.25 out front, and I have to evaluate this from 0 to pi over 2. All right, so at pi over 2, the sine is 1. So I'm basically going to get 1/2 times 152.25 minus when sine of 0 is 0. All right, so my answer is going to be this 152.25 times 1/2. So that is 76.125. Okay. All right, so moving on here. So here is my area that I'm trying to stay within. So let's draw that. Let's see, x and y. I am trying to do a circle with radius 1 and radius 3. I'm trying to stay between there. So radius 1 and radius 3. I am trying to stay when y is greater than or equal to 0. So y equals 0 is a horizontal line. So y equals 0 is here, and I am trying to stay everything above that. So I am basically trying to be in this area right there. Okay. All right. So if I write my double integral for that, remember one of our formulas was x squared plus y squared equals r squared. So that's going to be the square root of r squared, which is r. So that's replaced. Remember, I always have to put my own r and then dr d theta. Okay, so my r, I'm staying between circle 1 and circle 3. And my theta, I'm going all the way from here all the way to here. Well, that is 0 to pi. All right, so I'm basically integrating r squared. So that'd be r to the third over 3. I'm valuing this from 1 to 3. And let's see, plug into 3, I get 27 over 3 minus 1 over 3, so that'd be 26 over 3. So I have 26 over 3, integral from 0 to pi. There's nothing left to integrate there but a 1, and then I have d theta. So remember when we integrate 1 right there, I'll write it this time, but I'm going to get basically theta, and I'm evaluating this from theta equals 0 to theta equals pi. So when I do that, I plug in pi, then I plug in 0, and I subtract them. So I get pi minus 0, and then times is 26 over 3. So remember that fact right there, is that when you're integrating with respect to basically nothing there, except a 1, you basically just take these two boundaries and you subtract them. And that's what your answer is right there for that integral. Right? So that'll come up later. So this is just 26 pi over 3 for that space there. All right, so moving on to example 3 here. So this up here, let's see, we have e to the negative, we got x squared plus y squared if I pull that negative out. So that's negative r squared. So I'm doing double integral, e to the negative r squared. Remember, we have to put our own r, and then dr d theta. So let's figure out our boundaries. So bounded by this semicircle in the y-axis. All right, x and y. So that's solved for positive x. That means our semicircle is here, and the radius is 2. So this is where I'm trying to stay, in this little area right there. So you can tell I'm going from circle 0 to 2, but my angle. So this angle up here is pi over 2, and this one down here, I have to act as if I am going this way, and I have to go that way. And so I have to call this one negative pi over 2. So when I'm doing my boundaries for theta, I'm going to say negative pi over 2 and positive pi over 2. I know you're used to saying, like, this is 3 pi over 2 down here. Well, if I said, 3 pi over 2, I can't get to 3 pi over 2 without going through this area right here that I'm not supposed to go through. So I have to use negative pi over 2 to positive pi over 2. It's kind of like, think about if you're on a number line, and you're trying to get from here 0, and you're trying to get from here to here. You have to start at the low number and then travel towards the high number. So if you kind of think of this as like a number line right there, you're trying to go from one to the other, so you have to put the lowest to the highest. All right, and so let's go ahead and do our integral. So this is just a bit of u substitution. My u is going to be negative r squared. My du is going to be negative 2r dr. So I have negative 1/2 du equals r dr. So I will be replacing r dr with this negative 1/2 du, and then I will be replacing this negative r squared right here. All right, so let's see, I'm doing my integral. I'm going to put negative 1/2 du for my r and my dr, and then I have e to the u. Well, integral of e to the u is e to the u, so I have negative 1/2 e to the u, which is negative r squared. I have to evaluate this from r equals 0 to r equals 2. All right, so negative 1/2, r equals 2. So that'd be e to the negative 4 minus e to the 0. Well, e to the 0 is 1. All right, this is all just a big fat constant. So it's a big fat constant, e to the negative 4 minus 1, all in front of my negative pi over 2 to positive pi over 2, and there's no theta left, so it's just the integral of 1 d theta. So like I said before, remember I have negative 1/2 e to the negative 4 minus 1. When I integrate 1, I can just basically subtract my boundaries, pi over 2 minus a negative pi over 2. So it's pi over 2 plus pi over 2, so that would be pi. So my answer is negative pi over 2, e to the negative 4th minus 1, or that could be 1 over e to the 4th instead of e to the negative 4th. All right, and so if you wanted a decimal for this, it's about 1.54. Okay, so example 4, set up a double integral to find the area enclosed by this cardioid. So if you graph that cardioid, it looks about like this. It goes around, has a little hump right there. And so when you go all the way around, what you're doing is you're going from 0 to 2 pi. Because 0 to 2 pi is basically going to take you all the way around this thing. It's going to take you all the way through it. It's going to hit every outer part. All right. It's going to basically go from the center from 0 all the way out. And the R value, so you want to go from 0 to 1 plus sine theta. So this is the function that you're staying in. So you're not staying in a circle anymore. You're staying inside this cardioid. And we want the area, so we want to integrate with respect to 1. Oops, I got to put my own R, dr, d theta. All right, so I end up getting integral of r would be r squared over 2. And I have to do this from 0 to 1 plus sine theta. All right, so I'm going to pull out a 1/2 and leave that 1/2 there. So when I plug 1 plus sine theta in for r squared, I have 1 plus sine theta, and I have a square right there. Minus when I plug in 0, I get nothing. All right, so we still have d theta now, and we have 0 to 2 pi. All right, so I got to square this out. So remember, when I square that out, I get 1 squared is 1. Then I can multiply these 3 things together for my center. So it would be plus 2 sine theta. And then the last part is plus sine squared. Now, I can integrate 1. I can integrate 2 sine theta. It's this guy right here I'm going to have some trouble with. So there is a power reducing formula. So these 2 formulas that you have right here, sine squared, you can reduce it by, it is equal to 1/2, 1 minus cosine 2 theta. And cosine squared, if you should ever need it, is 1/2 and 1 plus cosine 2 theta. So we are going to use this power reducing formula replacement right here for this guy right there. Okay, so let's do that. So I have 1/2 integral from 0 to 2 pi, and I have 1 plus 2 sine theta plus the sine squared is going to turn into, I'm going to multiply this out, 1/2 minus 1/2 cosine 2 theta. All right, so clean that up a little bit. 1/2, that's 3/2, and then plus 2 sine theta minus 1/2 cosine 2 theta. All right. All right, so let's do our integral. So 3/2 turns into 3/2 theta. Let's see, plus sine. Integral of sine would be negative cosine, right? So I'm going to get, oops, let me erase that. So I'm going to get negative 2 cosine theta. And then let's see, integral of cosine will be sine, so it'll stay negative. Integral of cosine 2 theta will be sine 2 theta times 1/2 to counteract the 2. So that's going to, the 1/2 and the 1/2 will be a 1/4 right here. Sine 2 theta. Evaluate all this from 0 to 2 pi. All right, let me take a look and make sure we've done everything there. I have everything that I need. Yep, all looking good. All right, so let me see. Let's multiply that 1/2 through there just to get it out of the way. So I'm going to have basically 3/4 theta minus cosine theta minus 1/8 sine 2 theta from 0 to 2 pi. Now, let's take care of a few things right here. If I plug in 2 pi or 0 into sine of 2 times 2 pi would be sine of 4 pi, that's 0. Cosine of 0 is 0. This is all just going to go away forever and ever. Now, cosine, on the other hand, will not. All right, so here we go. Plug in 2 pi. So I have 3/4 times 2 pi. So that will be 3/4 times 2 pi minus cosine of 2 pi is 1. Let's see, minus 3/4 times 0 is 0. And 0 minus cosine of 0 is 1. All right, so let's see. So I have basically 3, so 6 over 4, 3 over 2 pi minus 1 minus a minus 1 turns into plus 1, so cancels out. So there's my answer, 3/2 pi. All right, let's see, we're going to set this up but not evaluate it. So we are trying to get the volume of the solid here that is above this cone. So here's my cone right here, 45-degree cone. All right, and let's see, and below the ellipsoid there. All right, so we gotta do some fixings here. So let's see, that cone, that would be z equals the square root of r squared, because x squared plus y squared equals r squared, so z equals r. So, oops, not r equals r, z equals r. All right, so that's the cone in, what's it called, polar world. All right, and then we had to figure out this ellipsoid. So let's look at this guy right here. So I got z squared. So we could do this a couple of different ways. Let's notice a couple things here. So this right here, that's 4 and then x squared plus y squared. So hopefully you can see that's 4 times r squared, right? So that's 4r squared. So I'm going to have z squared equals 25 minus 4r squared. And we are interested in the top part of the ellipsoid right here, right? So if I solve this for z, I'm going to get plus or minus the square root of 25 minus 4r squared. So I'm really only interested in the top part of the cone and the top part of the ellipsoid, so I can know that I only need the square root of 25 minus 4r squared. Right? So that's what we're going to stay between. So when I look at this space, the volume above the cone but below the ellipsoid, so this space like right inside right here, I'm going to do my double integral. The ellipsoid is on top, so that would be the square root of 25 minus 4r squared there. The cone on bottom, so that was z equals r. Okay. Oh, whoops, I forgot we're not doing double integral, the volume of that space. All right. Sorry guys, I was thinking about a triple integral, I think. All right, so I want to do that subtraction of that space. I want to do that in my integral right here. So that's going to be right here. So I'm going to have the square root of 25 minus 4r squared minus r. And so that's going to be basically like my floor and my ceiling, right? So this is like the top minus the bottom here. And then we always multiply by r, and we're doing dr d theta. Okay, now d theta is easy because it's going all the way around, so that's going to be 0 to 2 pi. Now my r is a different story here. I have to figure out where these two things intersect. Like, what r do they intersect at? I know I'm going from the center, but like, what's the circle like right here, the circle that they intersect at? What r value, what r circle are they intersecting at right there? So I have to do something with these two equations here. So let's go ahead and plug one into the other and see, kind of like a system of equations. So I'm going to plug this into here. So we're going to go ahead and get 4x squared plus 4y squared plus, if I square that out, it's going to, if I square both sides of this guy right there, like it says to do, I'm going to get plus another x squared plus y squared equals 25. So you can see that I get 5x squared plus 5y squared equals 25. So x squared plus y squared equals 5. So these things meet at a circle with the radius square root of 5 right there. So I'm going out from circle 0, or from the center, out to a circle with radius square root of 5. Okay, and so that's it. We just had to set this up. All right, and the last one here, set up a double integral, do not evaluate, to find the volume of the solid that's bounded by this paraboloid. All right, so let's see. So the ceiling, the floor is 0 right here. So when I do my double integral, I will be doing my ceiling minus my floor of 0. So z equals the sky to z equals 0. And so all I have to do is change this equation right here. Change that equation right there to 4 minus r squared, because x squared plus y squared equals r squared. So this is really 4 minus x squared plus y squared. All right, so 4 minus r squared times r, and then we got dr d theta. All right. All the way around. So all the way around means we're going 0 to 2 pi. And let's see. This guy, this paraboloid right here, if I do a little trace right here, like where is it hitting? I can tell from the picture kind of where it's hitting, but we should be a little bit more clear. Like I can, it's crossing at 2 most likely. But let's take a look at that. If I take this and inspect it a little bit more, z equals 4 minus x squared minus y squared. If I do a trace, like where is it hitting the x-axis? When y equals 0, it's z equals 4 minus x squared. So this factors into 2 plus x and 2 minus x. So it's hitting the x-axis at 2. And you can do the same thing for y. So you can tell that these are hitting at 2's right here. So I want to basically go out from 0 out to circle number 2. So 0 to 2. And that is it. So this is a pretty easy integral to do. I know it says not to do it, but why don't we just go ahead. So we got 4r minus r to the third. When I put that through, multiply this r right here through. So integrate with respect to r means I'd get 4r squared over 2. So that'd be 2r squared minus r to the fourth over 4 from 0 to 2. So I plug 2 into this and I get 8 minus 16 over 4 is 4. So we get 4. Plug in 0, it's just 0. So I'm getting 4, which is a constant. I still have my integral, 0 to 2 pi. And there's nothing left to integrate but just d theta. So remember, 4 times, and 2 pi minus 0 is 2 pi. So my answer is 8 pi. Okie doke. And that is it. So we'll see.